Hello class, today we're going to go ahead and cover section 6.4 on polynomial functions. So let's just go ahead and look at an example to begin with. A cross-section of a honeycomb has a pattern with one hexagon surrounded by 6 more hexagons. Surrounding these is a third ring, you can see this with the blue to the right on the picture, of 12 hexagons and so on. The total number of hexagons in a honeycomb can be modeled by the function f of r is equal to 3r squared minus 3r plus 1. Where r is the number of rings and f of r is the number of hexagons. Find the number of hexagons when r is equal to 4 and r is equal to 12. Okay, well they have the fourth ring kind of drawn for us here, and you could count it all up if you wanted to. But probably what's quicker is to go ahead and plug it into this equation here, which is actually a polynomial. So notice r is 4, so it's f of r, so now I'm going to plug in 4. So f of 4 is equal to 3 times 4 squared minus 3 times 4 plus 1. And I would just go ahead and simplify this. Well, following PEMDAS, okay, I want to do parentheses. There's parentheses written, but there's nothing inside, no operations inside the parentheses. So exponents is next. So I'm going to do 3 times 4 squared is 16 minus 3 times 4 is 12 plus 1. And then 3 times 16 is 48, minus 12 plus 1. And then I go ahead and add and subtract from left to right. So 48 minus 12 plus 1 will give me that f of 4 is equal to 37. So my fourth ring has 37 hexagons in it. Let's go ahead and use that polynomial again to figure out how many hexagons are in ring 12. So f of 12 is equal to 3 times 12 squared minus 3 times 12 plus 1. So same idea, I would have 3 times 144 minus 3 times 12 is 36 plus 1. 3 times 144 is 432 minus 36 plus 1. And so f of 12, our 12th ring, has 397 hexagons in it. So let's talk about what a polynomial is. Okay, a polynomial in one variable. So what it's saying is that there's only one variable in a polynomial. Okay, to be classified as a polynomial, you cannot have multiple variables. So either you have all x's or all y's. You just cannot have. You can't have like a's and b's. You can't have two. You could have just a, but you can't have both written in there. Okay, so maybe an example of a polynomial in one term, one variable would be y is equal to x squared plus 3x minus 2. Okay, what it's saying is y equals, there's only one variable written on the right-hand side. Okay, a non-example would be y is equal to ab squared plus a plus 2a plus b. This one has two variables, so that is not a polynomial. No variables in the denominator of a fraction. So essentially, you cannot have negative exponents or variables in the denominator. So once again, here's a non-example. Y is equal to x squared plus 1 over x. Okay, this is not an example because there is a variable in the denominator. If I could rewrite this using our rules, this could also be written as x to the negative 1, so you can't have negative exponents. So that means there's a variable in the denominator. We've already talked about degree of a polynomial, or we've talked about degree, but degree of a polynomial is once again the largest degree of a monomial in the polynomial. So it's whoever has the highest exponent. And then the leading coefficient. Okay, it's the coefficient of the term with the greatest degree. Okay. So let's just go ahead and look at an example where we identify some of these things. So we want to state the degree and leading coefficient of each polynomial in one variable. If it is not a polynomial in one variable, explain why. Okay? So you need to say, it is a polynomial, it isn't. Number one, I look at it, there is only one variable. There's no variables in the denominator, so it is a polynomial. So I can state the degree. Degree is the highest exponent. So this is really x to the 1, and this is really x to the 0, so my highest exponent is 4. And then my leading coefficient. Well, that's the highest, it's the coefficient of the term with the highest degree. So if I look here, this is the one with the highest degree, so the coefficient is the number in front, so that is 7. I go ahead and look at example 2. First of all, is this one a polynomial? I would say no, it is not a polynomial. And the reason that I would say that it is not a polynomial is because there's x and y. There's two variables. Example 3, I look at this one. I decide, is this a polynomial or not? And I would say that no, it is not a polynomial. And the reason is because my variable is in the denominator. And that is not allowed to be a polynomial. Okay. Let's go ahead and look at example 4 and 5. It says find the following values given the polynomial functions. So, little function notation. It says find f of b squared if f of x is equal to 2x squared plus 3x minus 1. Notice, b squared is in the spot of x, so wherever there's an x in here, now I'm going to go ahead and write b squared. So, f of b squared is equal to 2 times b squared squared plus 3 times b squared minus 1. Then I go ahead and simplify all the way. So I would have 2 times, well, b squared to the second would give me b to the fourth because I would multiply those two, plus 3b squared minus 1. And I'm just going to rewrite this without the parentheses. So f of b squared is equal to 2b to the fourth plus 3b squared minus 1. And there is f of b squared. Okay. 5 says find 2 of g of c plus 2, yes. So wherever, notice this is in the spot of x, wherever there's an x, I'm going to go ahead and put a c plus 2. And then after I do that, all of g of x needs to be multiplied by a 2. Okay, so I'm going to go ahead, it's 2 times, I'm going to write this part out with my c plus 2 in, so it's c plus 2 squared minus 4. Now remember, to simplify this first part here, you need to write it as c plus 2 times c plus 2, and you need to go ahead and FOIL. So we need to do that. So I would have 2, I would have c squared plus 2c plus 2c plus 4 minus 4 from this part. Then I would notice my 4 minus 4 will cancel out. And so I would have 2 times c squared plus 4c. And lastly, I would need to go ahead and distribute that 2. So I would get 2c squared plus 8c. And that would be my solution for example 5. Okay, before we go ahead and move on to the back side, if you have any questions about the front, write them on your note sheet. Make sure you come and ask me for clarification if you need more clarification. The next thing we're going to go ahead and talk about is the graph of polynomial functions. Okay, this is really important for you guys to understand what the graphs of each polynomial function looks like as you progress through math. You're going to be referring back to this a lot. Okay, so the first one, okay, a horizontal line, it's a constant function, okay, because this is y equals some number, so let's just say this is 2. This is a constant. Stays the same, so that's why it's called a constant function. The next one is our linear function. It's a degree of 1. So it's y equals mx plus b. Okay. This one is a first degree because on my x, it's really a 1. Once again, I could write, going back to my constant function, I could write this as x to the 0. We know anything to the 0 is really 1. So that's why this one is a 0 degree. Moving up, our quadratic function, we know that this is a degree of 2 because we have y. We all know that it's a y equals ax squared plus bx plus c. So it's a degree of 2. Now I know my cubic function. This one is a degree of 3. This function looks like this. Then my quartic function looks like this. This is a degree of 4, so that means it would have x to the 4th in it somewhere. And then my last function is x to the 5th. So some of you might be thinking, how can I tell the difference between these if I get the first 3, I get the constant, the linear, and the quadratic, but the other ones might be new to you. Well, here's some hints, and please write these down off to the side of your paper. Even degree. Ends go in the same direction. So if I go ahead, this 2, this is an even degree, okay, going in the same direction. They're going up. 4, even degree, always end going in the same direction. So that helps as an even degree. And then odd degree, one thing to note, is the ends go in different directions. Okay, so look at my degree of 1. 1 is going up, the other one's going down. Look at my cubic function. 1 is going up, 1 is going down. Same thing with my quintic, or my 5th degree. 1 is going up, 1 is going down. Another thing that helps, okay, is to figure out the number of degree. It says count the number of times it changes directions. So what you would do is count the number of changes in directions. So change in direction. And then you would add 1. That would give you the degree. Okay, so for instance, if I look at my quintic function, okay, we're going up, and then we turn and go down. So this is a change in direction here. Then I'm going down, now I'm going up. So here's a change in direction. Change in direction. Change in direction. There's 4 changes of directions, but if I add 1, I will get a 5th degree. But if I look at my quartic, change in direction occurs here, and here, and here. So that is 3 changes in direction, so 3 plus 1 is 4. My cubic function, change in direction here, change in direction here, 2 plus 1 is 3, so it's a degree 3. And lastly, I'm going to look at my quadratic. Change in direction only happens once. 1 plus 1 is 2. Okay. The next thing we're going to look at is end behavior of a polynomial. Okay, it's the trend of f of x as x approaches negative infinity and positive infinity. Okay, so when we look at the end behavior, what does f of x do as x approaches negative infinity? And what does f of x do as y approaches infinity? Remember, f of x is just your y. Okay, and some other things to keep in mind is on your axis, this is your x-axis and this is your y-axis. So to be looking as x goes to negative infinity, well, that's just going to the negative direction. So this x goes to negative infinity. You're going to look to the left. X goes to positive infinity, well, that's going to the right. Okay, so that is what that would look like. So let's just go ahead and look at some examples. So we have a degree of 2. Okay, this is an even function. It tells me my leading coefficient is positive. Okay, we've looked at this before. If this a is positive, we know it's opening up. If a is negative, we know it's opening down. Okay. Same thing with the odd example that they give us. Okay. So for instance, this is an ax cubed. If the a is positive, notice as you look from left to right, it is increasing. Okay, it's going upward. So that's how I know that this one is positive. And if I look at my odd function over here where my coefficient is negative, okay, as I look from left to right, it's going down. So it is negative. Then the other thing that we need to talk about, and they are written in here, is your end behavior. Okay, so what we're doing is x approaches infinity. We want to know what's happening to our y or f of x values. Okay, well, if I look at this quadratic, as x approaches infinity, as I look at my graph, okay, as we're going to the right, what's happening to my y values? Well, my y values are going up and up and up and up, and they're going to keep going up and up and up forever. So they're going to infinity. Now I look at as x is going towards negative infinity. My f of x values, well, my negative infinity, okay, my x is this way, so I'm looking as I go to the left. My y values are going up and up and up. They're going to go up and up forever, so they're going to infinity. Okay. Let's go ahead and just look at one other one. Let's look at this example here. So let's look at as x goes to negative infinity first. So as x goes to negative infinity, so I'm looking as I go to the left, my y values are going to keep going up and up and up, so it is infinity. Then I go ahead and I look at as my x values are going to positive infinity, so my x values are going positive. My y values, if I look on the graph, are going down and down and down. So now in this case, since they're going down, they're going to negative infinity. Okay. So we're going to have some examples where we're going to do a little bit more of this right here below. So for each graph, describe the end behavior, determine whether it represents an odd degree or an even degree polynomial function, and state the number of real zeros. Okay? So this one, let's just start out, is it an odd or even? Well, first thing I notice is that both ends are going in the same direction, which tells me that it's an even degree. And now I actually want to know the degree. Well, in order to figure out the degree, I count my change in directions. 1, 2, 3. 3 plus 1 gives me 4. So it's an even degree of 4. Now my end behavior. So we want to look at as x goes to negative infinity and as x goes to positive infinity, what happens to those f of x values or our y values? Okay. Well, as x goes to negative infinity, so we're looking as we go to the left. What happens to my y values? Well, they're going to go down, and they're going to keep going down and down and down, so they're going more negative, so they're negative infinity. And as x goes to infinity, so we're looking as we go to the right, following the function, my y values are going down and down and down, so once again going to negative infinity. And the last thing we need to talk about is the number of real zeros. Remember, zeros equal the solutions or the roots or the x-intercept, so I go ahead and count those up. So there's one here and here. So there is 2 real zeros. Okay. Example 7, I go ahead and look at this one. First of all, I decide is it even or odd? Well, both ends, once again, are going in the same direction, so that makes it an even degree. Then to figure out, well, you guys know that this one's a quadratic, so you should know it's a degree 2. But the other way is there's only one change in direction. 1 plus 1 is 2. So that's how I would get that. Now we go ahead and look. As x goes to negative infinity and as x goes to positive infinity, what happens to our f of x or y values? One thing to notice with even functions is that your end behavior should be the same because they're both ending in the same direction, okay, because they both are the same. So as x goes to negative infinity, so I'm looking as we go to the left, so I follow my function to the left. What's happening to my y values? They're going up and up, so they're positive, so they're going to infinity. And then as x goes to infinity, same thing, keeps going up and up, so going to infinity. And now how many solutions? Well, these are x-intercepts. If I look on my x-intercepts, my x-axis, my graph or my function never touches it. So in this case, there is no real solutions or zeros. There would only be imaginary or complex, like we talked about last trimester. And lastly, example 8. So first of all, I have to decide if it is even or odd. Well, I have one end going down and the other end going up. Since they're going in opposite directions, I know it's an odd degree. And then I need to figure out what degree it is. So how many change in directions plus 1 is there? So there's 1 change, 2, 3, 4. So this is a 5th degree polynomial. And now, as x goes to negative infinity, f of x, what happens to that? And as x goes to positive infinity, once again, what happens to f of x? Okay. Well, as x goes to negative infinity, so we're looking as we go to the left, following my function, we're going to go down and down and down and down. So my y values are going more negative, so it's a negative infinity. And then as x goes to infinity, okay, so now going to the right, following my function, going to keep going up and up, so it's going to infinity. And the last thing I need to do is figure out how many zeros are there. Okay, so this case, I would go ahead, count on my how many x-intercepts I have. There is 1, 2, 3, 4, and 5. So there are 5 real zeros. Okay, so that's it for the notes today. Please feel free, if you have any questions, write them down and ask them tomorrow in class. Otherwise, have a great day. Talk to you later.